Okay, so some bookkeeping things. So daily homework 9 is due next Tuesday. Okay, we're also gonna have an extra class on Monday. Extra class on Monday.
Do you know the times yet?
It's gonna be the
Love that time.
yes, 1:20 to 2:10. And then we can do then the 4:20 to 5:10. If you want, I can go to 5:10 to 5:10. I mean 5:20 to 6:10 if that helps.
I mean, I can make one of those.
Okay. No one, okay, I don't mind doing the 8:31, but no, 8:20, no one showed up, so I just was on stuff, grading stuff. I don't know if it's just because you want to sleep in, which is perfectly fine, okay? Or whether there's a conflict, I don't know which the status was. But since no one showed up, I officially declare that time dead, unless there's like, has to be 8:20. I'm definitely a morning person, I'm not an evening person. I don't, brain me not work good night. Brain bad, brain good night. Okay, so let's go on. What we're doing is following. We're looking, so last bad time. Okay, meaning yesterday, what did we do? We looked at the 3D. Infinite well. I know a lot of people couldn't make the time yesterday, which is perfectly fine. Make certain you watch that recording because I worked it out in detail. And one reason why you might want to look at it is that this homework right here is really the two-dimensional version of this. And so if you do what we did in 2 dimensions from that lecture yesterday, that you'll find that very helpful if you weren't able to come. So make certain you watch that video and I sent you all the link to the page. Okay, so we had this. This is X, this is Y, and this is Z. And a 3-dimensional box is going to be a regular box like this. And the 1D, so this is a 3D infinite well. And this is our 1D infinite well. Remember what we had here. This is 0. How do we make this an infinite well? What do we do with the V naught values? Yeah, they go off to infinity. So we said all this now here is going to be infinity, and all this over here. Right, it's going to be infinity. So what's going to happen in this case over here then? And then we have V equals 0 on the interior. What do you think is going to happen then in the 3-dimensional version of this?
Inside the box, V equals 0.
So inside the box is 0. Yep. Okay. And everywhere outside here, your V goes off to infinity. That's what it means to be an infinite well. And in this case over here, in the 1D case, what did we have? We had that this E equals h bar squared pi squared n squared over 2ml squared. And when we go to the 3D case, what do we have? We have the exact same thing, but now we extend it to the Y and the Z directions. And so if you watch that video, you'll see where we do all the details on that. So in the 3D case, we have the energy here is h bar squared over pi squared over 2m. But then, if I call this length in the x direction A, if I call this length in the y direction B, and the C direction C, we end up with this. We end up with nx over A squared. So that's just like this n squared over L squared. It's that exact same term. And then we just have the Y. And then we have the Z. So if I just wrote that down without driving it, I don't think any of you would even question that. If I just said, look at what do you think is going to happen if you go to 3 dimensions? You're going to get this. I think almost everyone would say, sure, makes sense. It does. Now, what do you think we're gonna do with the A, B, and the C values? Make life easier for ourselves. We're gonna make them equal and let's call them L. So what I'm gonna do is take the case. Where A equals B equals C equals L. So what can I do? If these are all the lengths are the same, I can pull them out. I'm gonna replace it with an L. So I get this. And we're gonna get a brand new feature. Now this really looks exactly like that equivalence. This feature here is the exact same thing as this feature here, and then we just have all the three n numbers there. So now we have three quantum numbers. E on the quantum numbers. And X and Y and Z. So now if you want to specify a state, you don't have to give three quantum numbers for this. And we're going to get a unique feature, and let's see what that unique feature is going to be. So does this make sense? Again, if you haven't watched the video, watch the video. It's not hard, it's what we've done before, it's just longer. Okay. Okay, let's look at an energy level diagram for this. This is E. Okay, what's going to be the ground state energy for this? Again, remember, what's the lowest the energy values can be? 1. So what it's going to be the NX, NY, and NZ for the ground state.
Should we do it as a sum of the terms? That way it's just giving
What do you mean?
like the lowest state for each of them would be n, x, and y, and z equals 1. But you have to add them together, right? Because you have.
Okay, we're going to treat, well, we're going to specify the energy by the quantum number. So I should put this down here. So often, meaning almost every time, in quantum mechanics, E is labeled with its quantum numbers. So I call this E equals NX, NY, and Z. So the lowest state is going to be E 111. So this will be the lowest state. This will be E 111. This is my ground state. So what does that equal? Let's do some crazy math.
3 times.
Yeah, 1 squared plus 1 squared plus 1 squared. Okay, 3. Okay, so this is going to become 3 h bar squared pi squared over 2ml squared. Okay, now here's where the fun begins. What is the first excited state?
And isn't there three that all have the same energy?
I agree. What would they be?
E211, E121, E112.
Yeah, so I could have E112, I could have E121, or I could have E211. They're all distinct states, but they have the same energy. Now this is given a new feature here. So when you have the same energy, but different quantum numbers. The energy level is said to be degenerate. So degenerate just means it's the same energy, different quantum number, so they're different things.
Smokes and drinks a lot.
Yeah, it goes and smokes and hangs out in, malls and trips old women, in the parking lot. They're degenerate. It's completely degenerate. Yeah. Awful. Okay. Listening to music that doesn't rhyme, bad.
Really atrocious.
Terrible. Yes.
Does this have anything to do with meaning of degenerate semiconductors?
Considering I'm not familiar with what degenerate semiconductors, all right. It does, I'm not familiar with what they are, so I don't know. But my guess would be, since it's being used in a physics context, I probably guess it does. I don't know. Okay. Okay, what would that energy level be?
Oh, the energy, okay.
Yep.
Six.
Six, okay. I know that would cancel to give a 3, but I'm gonna leave this 2 in here just so everything has a 2. So this is gonna be what? This is gonna be, these values are gonna be the 6 h bar squared pi squared over 2 ml squared. Because we're gonna have 1 squared plus 1 squared plus 2 squared, which is 6. Okay. What's next? What's the second excited state?
Ooh, excellent.
Okay, so now we have a question. Is it 1, 2, 2 or 1, 1
It would be.
or 1, 1?
3.
3? Which one?
Uh,
We have to work it out. Okay, we get to do crazy math. Okay, let's try 1, 2, 2. 1 squared
one,
plus 2 squared plus 2 squared.
9.
I call that 9. Okay. Let's try next one. 1 squared plus 1 squared
2,
plus 3 squared.
11.
I call that 11. Crazy, I know. It's just wild. Okay, so this is going to be the 113. Not going to be that at all. It's going to be 221. Okay. And how degenerate will that be? Triply degenerate.
Certainly the 3 quantum numbers can't the most generally have be 3. Oh, fun.
Okay, we're going to find out why. Because suppose n is gigantic. Okay, that's when you're going to start getting things.
There's multiple ways to.
And then what did we say this one is equal to? We said that this is going to be. It was 9, right? Yeah, 9. 9 h squared pi squared over 2 ml squared. Now what's next? Again, we have a choice. It could be 113, but it could also be 222. So which one is that? The 113 or 222?
113.
113 is next. Okay. And this one will be the 11 h squared pi squared over 2 ml squared. Okay, we'll stop after the next one. Okay, because it starts getting harder. Okay, what's going on? It's not hard, but it's just kind of a pain. What's next?
222.
Yeah, and how many of those are there? Okay, so it goes back to this. This is going to be this 12 h squared pi squared. 1 ml squared. Okay. And you can go on and on with this. Okay. So what would happen if I fill this up with, let's say, 20 electrons? 20 non-interacting electrons. So let's put this over here. So if 20 non-interacting electrons are placed in a 3D box. Okay. What is it to energy for the system?
Does non-interacting mean that Pauli exclusion still applies?
Yeah, because all the Pauli exclusion principle only depends on the spin. Doesn't depend on anything else. The non-interacting means what am I doing about the electron repulsion? Out of there, because basically they're not, it messes up the sugar equation, it doesn't look like this. I've turned off the Coulomb repulsion, which is not as bad as you realize it is until you have to, it takes a lot of physics to realize a lot of physics, to find out why that is sometimes not as stupid as it seems. Okay, so what do we get? So I grab one little electron. Where does my little buddy go? Yeah, my first little electron goes here. Hey, where's my second little electron go? It can go here, but it has to be down. Where's my third little friend go? Okay, it's gonna go here. There's a complicated principle connected with the Pauli exclusion principle that I don't want to get into. It turns out that usually what's going to happen when you put in the fourth one, it's going to go where? It's going to go here, going in the same direction as the spin. There's a very technical reason for that. That is well beyond the scope of this course. So if this happens, where do you think the next one goes? It's here. Next one. Yeah, then down, down, down. So we have we've gone through 8. We have 12 more to get rid of. And what do they do? Well, they keep on filling like you think they would. We have this here. We have this. Okay, are we done?
Yes.
Okay, so that's what the system would be. So if you're to write this as the energy, then what would the energy be?
81 not is h bar squared I squared.
Okay, well, I'm going to write it in terms of that, but we won't do that. Okay, so what are we going to have? We're going to have 2 E11 plus.
Oh, I did bad math. Plus,
Yeah, why don't I have to put in 2 in each of those ones here and put in all 3 terms? Because their energies are all the same. So I can take 6 times one of these energies. I'm going to do this one for no good reason. So I'm going to have 6 times E112 plus 6 E122, then 6 E113. Now, if I wanted to, I could put in those values that you said. I could put in the I could call this value here like an E naught, and then calculate them all up.
it's 162, by the way.
It's what?
It's 162.
Okay.
There's 2 electrons.
162, you said?
Yeah.
Okay. Times this h bar squared pi squared. Okay. Now, what would be the first excited state for the system? Yeah, and I have to take one of these electrons here and kick it up into here. Right, so the ground state energy, I'm sorry, the first excited state energy would be this. And the exact same initial format. I have 5 E112, I'm sorry, E113 plus E22. Makes sense? What would happen if instead I had 20 non-interacting pions which have an S equals 0? They're going to be
On the bottom.
bosons, and they can all then collapse into this ground state. Okay. So the thermodynamics for bosonic systems, the thermodynamics for fermionic systems are entirely different. And next spring, if you take my course in physical mechanics, I will tell you all about the differences that occur there. And that's going to be a gigantic section of the classes of the thermodynamics of fermionic and bosonic systems. Okay. It's like half the class almost.
When did we get L squared? I thought it was just,
Okay, it isn't, was it L squared? Because remember all those, we had the terms coming in like this,
they were all squared.
squared,
Right,
where we said A equals B equals C equals L, then pull it out.
thank you.
That makes sense? Now, what I want to do is, let's treat this as a first, one other thing. To kind of give you a little hint of what's happening with these, why you can start treating these as kind of non-interacting. So, can these two, if these, let's say this electron here and this electron here, let's say they collide with each other. What would happen? Nothing, right? Because basically the Pauli exclusion principle will prevent these from doing anything. So actually what happens is the particles down here, they are interacting, but when you start looking at the exclusion principle in proper form, it gets a lot more complicated. Is that basically these right here, normally if you think of two things colliding, you think of them as scattering out or as well. But you can see that processes like this are going to start being limited. It's basically, they can't, there's nowhere else for this fellow to go. Because it's here, everything else is Pollock is filled. Again, I had in grad school, I had one class, and almost the entire class was basically dealing with that. Turns out there's some details, and you get good physics too. Questions? Okay, so now let's actually use this to make a very important model. Let's treat a metal as an infinite 3D box filled with n non-interacting. We give this a name if they're non-interacting. What does it mean? It means that there's really no forces acting on the particles. So we call this the free electron theory of metals. So this model. It's called free electron theory of metals. Okay. And once we're done with this, we're going to put, well, you're going to do a homework problem. You're going to put protons and neutrons in there, then you're going to have the free nucleon theory of nuclei. Okay. So this is also called the electron gas. Okay. This is basically going to be a gas of electrons. The free electron gas. So here's our metal. You're gonna have all these little electrons in here. We have that and electrons in the box. Now, how big is that going to be for a metal?
There.
I don't know. Let's actually maybe give it a number, maybe like 6.02 times 10 to the 23rd. It's going to be like a mole of electrons. It's going to be something preposterous. Okay, if we start putting in that many electrons, do you think we're going to have numbers like 1, 1, 2?
Yes,
We will, but what else will we have?
very large.
You know, 10 to the, 10 to the 17, 10 to the 18, 2 times 10 to the 14, things like that. Okay, we're going to start getting really preposterous electron numbers.
The rest of the class should be plotting out all the various energy levels.
That's all we're going to do. Okay, we're going to make this diagram go up to Avogadro's number. Can be a little boring, but at least you know what to expect every day. You just keep on adding to this energy level diagram.
Maybe once in a while we'll find an energy level that has more than 3 degenerate.
I think we're gonna do that right now. We're gonna get a beautiful picture. Okay, what am I gonna do next? This diagram that I'm gonna do in this argument is used absolutely everywhere in physics. So you're gonna get a lot of mileage in this class. If you take anything in astrophysics, you're gonna use it there. If you take the StatMech course, you're gonna use it there. This argument, condensed matter physics, solid state physics, use this argument absolutely everywhere. Okay, so let's see what happens here. So how can we account a large number? This is what we're doing. This is absolutely beautifully. I'm gonna plot NZ here, and Y here, and X here. So where would be the 111 value on here?
Just off the origin.
Yeah, and basically I come over here to 1, this would be 1, this would be 1. I have a little dot there, so that dot would be 111. And I would have all these other dots here like this. These would be the low level energy level values. Low N values. But eventually what's going to happen? I'm going to have these N values be gigantic. And I'm going to have some dot out here. And so this dot value right here. Okay, what I'm going to do is I'm going to define N squared to be by definition NX squared plus NY squared plus Z squared. So this N here, I'm going to call the length here right here. This is N. So this is the point NX, NY, and Z. And then what would my energy level be? My energy level would be this. Oh, I'm going into general odds territory. Go over here. Let's look over here. Right, we're calling all that here N squared, and these N values are large. Well, where else in this picture would I have the exact same value of N?
Sphere with radius N.
Yeah, I would have anywhere on a sphere here like this. This is the sphere of radius N. And it's not quite a sphere, it is
I think it's eighth of the sphere.
an eighth of the sphere, so it's 1/8 of the sphere of radius N. Right? And anywhere on the sphere here, you're gonna have the same values of E. So all the states, meaning all the NX, NY, and NZ values on the sphere, on the surface of the sphere, has the same N value, and hence the same energy. So now look, we don't have any more, it's not like we have 3 degenerate states. We now have some preposterous number of states. It's going to be a continuous almost. Okay.
I think you've also squared on your NZ there. Energy. Down below.
Oh, yep, everyone's fair, screwed up here. I have this guy here, there shouldn't be. Keep me honest. And I declare this marker to have gone to marker heaven. This one here.
That was solid.
Okay. That's what happens. No, don't, it's gonna dump on your hands because it feels like that. Don't do that. Okay. Unless you want to have marker hands. It turns out I have marker hands. Ends up giving you superpowers. Yeah, see, because the marker hand, I can actually pass this marker through my head. Well, see, I know. Okay, I would be able to do that if I didn't have this marker hand. Okay? Amazing superpowers we got. It's like I can just let my finger too. Okay. Crazy.
Into my nose.
Yeah. Now we can do something else here. I'm going to actually give this a little thickness here, like this. Maybe it's a good thing we change all the markers. I'm going to give this a little thickness here. So this is a thickness to this spherical surface. And if this is n here, what do you think I'll call that thickness if it's tiny? I'll call it dn. Okay, so I'm going to call this thickness here, I'm going to call this dn. And so what do I have here? Basically, any arrow that's in that region there is going to have the exact same value. So what we're going to say is that the number of states, the number of energy levels that have the same value of n and hence the same energy. Okay, is equal to the volume of the volume of this 1/8 of the spherical shell. I'll say 1/8 of an onion layer. I'll call this an onion layer. Okay. So what would be the volume of this onion layer here? Imagine I had the whole thing. Imagine I had the whole sphere. Imagine I didn't have an eighth of it.
It's the larger sphere minus the smaller sphere.
You could do that, and if you use calculus reductions to something simple, and I'll give you a hint. Think back to physics 126, when you had variations on this, like in Gauss's law.
You do like surface area.
You do the surface area, which is okay. Okay, let's talk to you physicists and engineers. Okay, who are now juniors and sophomores. Let's have this crazy hypothetical structure I like to call sphere. Okay, what is its surface area?
4 pi r squared.
Thank you. Okay. So you take the surface area 4 pi r squared. What's the r in this case? N. So that's the surface area. Then you multiply that by the thickness. And so you take the surface area times the thickness. That's going to be the volume of the whole, basically the big onion layer. How much of the onion layer do we have? Well,
1/8.
1/8 of it. So we have this. Okay, so this is going to equal the number of states with the same value of n.
So are we just, sorry, are we having n just be large enough that even though the energy states are discrete, they're functionally continuous?
Yeah, so in other words, we have these small ones down here, they're certainly there, but the dominating terms of the energy are going to come from these large values. Remember, we're putting in 10 to the 23rd particles.
But they still are discrete, right?
Yeah.
It's just
Yeah, but they're going to be so,
No.
they're going to be, the number is so large, it's a lot. If you have 1 million, and I give you $1, or let's say 1 penny, you still have 1 million. The difference between 1 million and 1,000,001, who cares? Okay. Does that make sense? Let's put it all together now. Okay. So now let's calculate the energy of the system. We calculate the energy of the system. So the exact thing would be this. I would have basically the, now you're gonna do the ground state. I'll calculate the ground state. Energy of the system. So I said the energy of the system ground state would be what? I has to sum up over all the nx values from 1 to some nx max. Sum up all the ny values from 1 to ny max. Sum up nz from 1 to nz max of this e and x and y and z. Tell me why you have to put a factor of 2 in there.
Because 2 electrons per state.
Because of the spin. Okay, yeah, spin up and spin down. So this is due to spin up and down. Now, what are we going to say that equals here? The dominant terms are coming from these large values of n. So I can say that this is, to a very good approximation, and again, to say that this is, again, this is basically exact. Okay, these smaller ones are not having any effect here. It's going to be what? It's going to be the energy of one state. Well, this is the energy of one state of with n. Now, how many of these states do we have? This many here. We're going to have this 1/8. I know that I can cancel. I'm just putting it in here to make it obvious. Okay. This is the number of states with the same energy. The same value then. We have to multiply by 2 here for spin. And then what would we do with that quantity? So, okay, let me say one thing that I'll get there. So this quantity right here, that quantity right there is the energy actually in this shell here. Okay, go ahead.
What do you mean by nx max?
Well, we don't, that's a good question. And that's going to be a little more, it's going to be more obvious when you deal with that. Hold that
Well,
thought.
I'm like, isn't the ground state just one energy level or?
Well, this is, but this, remember the n is going to, nx can be 1, 2, 3, 4, 5. You're doing the whole system.
Okay,
So remember when we had the one state we put in the 20 electrons, those n values went up to, I think we went up to 3.
so you have a general form and we don't know
Exactly.
how many
Yeah,
electrons.
exactly. It's going to be connected to the Fermi energy. Okay. Crazy. Okay. So that's the energy just in this level here, in this shell. So if I want the total energy then for the system, what do I have to do?
Integrate
From where to where?
with 0 to m.
Yeah, basically, I can basically say, I know the n value doesn't get to 0, it gets to 3. But my n is going off to some preposterous number, so I can call it 0. So what I can do is I can integrate here from 0 to some n max value. I don't know what that n max value is yet. That's going to get a new name in a little while. Okay. Okay, so let's crank that out and see what we get. Go ahead.
There's no point in using 3 instead of 0 because it's going to be function the same.
So what happens here? The 2 and the 4 and the 2 cancel the 8. And I'm gonna write this in a way that looks a little odd. There's a reason I'm writing it like this. I'm gonna say that this energy here is the ground state. I'm gonna cancel the 8 stuff. I'm gonna write this as h bar squared pi squared 2ml squared. I'm pulling that out. I'm gonna leave my pi here. Then I'm gonna have this integral then of n to the 4th dn. I know I can make this pi cubed. I don't want to, and there's a reason. Just hold that thought. This is going to go to some n max. Hey, what's that crazy integral called? Okay, that was a little long for everyone here. That's just, that should really be coming out of your mouth really quick.
I was looking for it.
Okay. So this is gonna be 1/5. And maximum fifth power. And what I'm gonna do is I'm gonna rewrite this in an odd way. I'm gonna write this as, I'm gonna put the 5 out here. I have an h bar squared pi squared 2ml squared. I'm gonna take 2 of the n's and put it here. I'm gonna call this n max squared. And then what am I left with? I'm left with a pi and an n max cubed. What on earth does this look like? So what's happening? I'm putting in all these particles, all the levels are filling up. Eventually, there's going to be some maximum level up here. Okay, what's that maximum energy level? It's going to be given by this. Okay, hey, let's give this a name. Let's call this maximum energy level the Fermi energy. We're going to call this guy here. This is the Fermi energy. Okay, and I'm going to call this EF. Okay, it's your maximum level here. Now, here's, okay, the Fermi energies, in this case here, it makes a lot of sense. It's going to get mucked up pretty. This calculation I've done here, I'm assuming all the particles are down as low as they can be. This is really the temperature equals 0 case. I'm assuming that there's the temperature of the system is something hot. And so it turns out that the Fermi energy is a beautiful meaning when the temperature equals 0. When the temperature is 0, it is your maximum energy level that the electrons or fermions can go to. When the temperature is not equal to 0, it gets a little more murky. It gets more normal. Don't worry about that for yet. Okay, so I can rewrite this. The energy of this ground state of nothing. 1/5 EF, the Fermi energy. Pi and max cubed. Now, how many particles did we say we put in there? How many electrons? It rhymes with n. N, that's correct. We put in n particles in there. It'd be really nice to somehow get n in here. So the question is, how can we write n? So how is n related to n max? Okay. You know how to do this. Just vary the arguments now. Let's draw our little picture now. This guy here. This guy, we said the volume of this guy here is this 1/8 4 pi n squared dn. We said the volume here is the number of states. Okay, so how can I relate that to a capital N?
N is equal to nx max, or yeah, nx max plus ny max plus n.
That is, but I don't know if the nx max is or the n1 max or the nz max is. But what you said is true.
I like being right.
Well, if I take this and multiply it by 2, what is it? That's the number of states, or in other words, the number of electrons in this shell here. So if I want the total number of electrons, what would I then do?
Great that.
0 to n max. So if I do the following.
I'm very challenging, Nicole.
I mean, I just want it. So we're gonna say that the number of electrons n is gonna be, I'm gonna take twice this value. So I'm gonna take twice this 1/8. 4 pi n squared again here. So this right here, this is the number of electrons with the value n. Well, the total number, if I then sum these up from then 0 to n max, I have it. So what does that give me? All the 8s go away. I can pull out the pi. What do we get?
Yeah, 1/3 and 2/3.
It's gonna be pi over 3 n max cubed. Okay, now we're gonna get an extremely profound equation that occurs all over physics. I'm gonna take this value here. Well, I'm gonna multiply the top and bottom by 3. What do I know about all that? That's that. I take the 3 out front, so I get 3/5 and comes in Fermi energy. This is used absolutely everywhere in physics.
Still only at equal 0.
That's only at t equals 0. And if you take stat mech in the spring, I show you how to actually start going past n equals 0. You have to use something called the Sommerfeld expansion. Beautiful. The derivation of the Sommerfeld expansion, there's a little bit of an edge. Okay. And what's going to happen when you do protons and neutrons? You're going to have a nucleus. You're going to fill up with protons and neutrons, and you're going to get the exact same expression. Okay. Now, one of the first applications we're going to do, and not today, I'm going to show you how to calculate the Fermi energy for things, and we're going to get a good value. So for you people in Elmo and stuff, give me a typical Fermi energy value.
0.11. 1.1.
Give me units.
Oh,
It's going to be in the EV range. Okay. Typically, you get like, couple EV as a typical. I'm going to show you how to actually calculate that. It's actually a good calculation to do. Okay. It's not going to be hard. It's kind of nice. And then what we're going to do, we're going to make the box really, really big, on the size of a star. It's going to be filled with electrons. And what's gravity going to try to do? It's going to try to compress it. It turns out that's ultimately how we're going to get a weight to life. Because when you look at a star, what do you usually forget? What do you just completely throw away? Don't worry about. You don't even worry about the electrons. And you don't have to worry about the electrons until the star starts to collapse. And if you have a puny sun, like we do, okay? Because, okay, if you're, let's say you're in some back alley, some guy with a trench coat, opens up his trench coat and says, want to buy some solar real estate? And it's a really big, massive star. Don't buy it. That's bad real estate. It might come with a good price, but that's bad real estate. You want the puny, wimpy star. Okay, don't go buying stars in back alleys. They're bad. It's bad real estate. Okay, have a good day.
Do you pencil, man?
Yes.